So let's get into a little bit about what makes the analysis difficult. So now that we've talked a little bit about the analysis, the hydrologic tools, the hydraulic tools, and the economic inputs, I'll talk a little bit about what makes the analysis difficult. Well, one of the main things that makes it difficult within the Sacramento Basin is the levee system. That, for flood risk analysis, what we really are interested in is what's that stage frequency curve at the structures themselves. So, what's the likelihood of various flood depths and the probability of those flood depths. Within the Central Valley and the Sacramento Basin, we're developing water source profiles within the stream, and that streams are confined by the levee system. And so there's not always a one-to-one relationship between the water source elevation in the channel and then the floodplains. In some cases, there are. There's enough volume in the river, and the floodplain is confined enough that if there is a levee failure, they'll equalize. There's enough volume that fills, and so it is a one-to-one relationship. But in many cases, it's not. And where it's not, we have to rely on development of an interior-exterior relationship. So a channel water source elevation to a floodplain stage relationship. And we do this by simulating, using our hydrology models and our hydraulic models, and simulating various levee breaches and getting, for a given event in the system and the levee breaks, what's that volume that enters the floodplain, and use that to get the water source elevation. And so through the series of multiple steps of routing an event through the system, breaking the levee, looking at the amount of volume through that breach that enters the floodplain, and computing a water source elevation, we can develop a channel water surface elevation relationship for each of the index points for each of the impact areas that I had shown before. Another part of the analysis that is really complex is our reservoir system. Some of you, this is kind of a little bit of a quiz that I like to ask of, who knows this reservoir? It's Shasta. It's about a 4.5 million acre feet reservoir, water supply, and flood control. We go through the Central Valley. Over here, we have Oroville Dam. Many of you saw Oroville Dam in the news in the last few years that in 2017, during flood releases, there was an incident, and the integrity of the spillway actually was compromised. Ultimately, water came over the emergency spillway, which you kind of see right here, caused erosion, and ultimately the evacuation of much of the area downstream, Oroville, Yuba City, and Marysville. So definitely a very scary event, and one that's really had the focus of a lot of work since then on just how do we improve the reservoir performance and just modernize the systems in some ways. We also have New Bullards Bar Reservoir, 2 million acre feet reservoir, owned and operated by Yuba Water Agency. So what's interesting about this, that the other reservoirs being Section 7 reservoirs, a federal flood control space, but New Bullards Bar is owned and operated by Yuba Water, and it does have it is a Section 7 reservoir and has a flood control space. And then we also have Folsom Dam. So Folsom, a 1 million acre feet reservoir that. Okay, so let's start over on that. 2, 3. Okay. What also makes the analysis within the Sacramento Basin difficult is our highly regulated system. And so we've got a lot of major flood control reservoirs that really, compounded with a lot of the uncontrolled runoff areas, the areas that aren't regulated, make development of regulated flow frequency curves really complex. Many of the major flood control reservoirs actually are Section 7 reservoirs, and so there's a federal flood space, but the reservoir is owned and operated by other local entities. And so We just kind of look at some of the reservoirs within the system. We've got Shasta, about a 4.5 million acre feet reservoir, owned and operated by the Bureau of Reclamation. We've got Oroville Dam by the state of California. I think many of you have likely have seen Oroville Dam in the news lately. That in 2017 there were issues with the spillway integrity, and ultimately resulted in the need to evacuate many people downstream. And so definitely the last few years, a lot of attention in Oroville and looking at the need for any potential enhancements to the facility, and also updating of the water control manual. And Oroville is about a 4.5 million acre feet reservoir. We also have Newlor's Bar. What's interesting about that is it's owned by a local water agency, Yuba Water, again, for hydropower, conservation, but also flood control. About a 2 million acre feet reservoir. And then we have Folsom Dam, which is just upstream here, about 20 miles from Sacramento, on the American River. Folsom is about 1 million acre feet. And what's really neat about Folsom is it has recently had a new auxiliary spillway added for the process of raising Folsom Dam. And so it has a new water control manual. And again, what's cool about that is one of the first water control manuals to formally integrate forecast-based operations. And I think about forecast-based really being, we're looking at volumes that are much longer than the time of concentration of the watershed. So 5-day volumes to make reservoir release decisions. And so it really was a precedent-setting event. But again, all these reservoirs make the analysis of the regulated flow frequency curve much more complex. And so how we deal with that is development of an unregulated to regulated discharge. This is something you can enter directly into HEC-FDA. And so how we develop this relationship is, we have our volume frequency curve, and we've got our statements of volume, the likelihood of the 100-year volume, 200-year volume, 1%, 0.5% volumes. But what we need to do is get a model or representation of the system and how it performs for a range of different events. And so we've built a really detailed reservoir simulation model, a ResSim model, that includes all the physical features of the reservoirs in the system and includes all the operating rules from the water control manuals. And we simulate a variety of historical patterns, some of our largest flood events, through the reservoir simulation model, and scaled versions of those historical events as well. So we scale, for example, the 97 event. I talked about being a major flood, thought to be around a 100-year event. We take that event and scale it up by 5%, 10%, and simulate those flows through the reservoir simulation model, and pair up the unregulated volume and the peak simulated flow, and using those simulation points to find an unregulated to regulated transform that we can integrate into the risk analysis and ultimately show a regulated flow frequency curve. And that's really what we want. We want the likelihood of various flows in the channels to drive our risk analysis.